Hello and welcome back to the continuation of tutorial 12, the static mixer. Okay, so remember this case is a 3D case. When launching Fluent, do not forget to launch it in 3D mode. Okay, so I will open the file. Okay, so this case is inexpensive. I wish I would just show you how to run one case, and then I have solutions that I would use to show you different scenarios. So we have here in the case presentation, you have how to set up the case. Okay, so it's relatively straightforward. So we're going to use incompressible flow, okay, with no temp energy equation, or with energy equation but density constant. Okay, so there is only thermal diffusion. Okay, just to show you, it will be kind of a passive scalar, equivalent to a passive scalar. So go here, and this is our inlets, outlets. Okay, and we have our walls. Okay, so this is our geometry. Okay, and remember that you have here the vertical workflow. So let me revisit that again in 3D, nothing changed. So pressure base, steady solver, enable energy. Okay, then here I choose my turbulence model. So for the sake of simplicity, just to show you at the beginning, I will choose the standard K epsilon with curvature correction. Okay, I will leave it like that. Then materials, just a reminder that here, okay, remember that I'm using density constant, so I just want thermal diffusion. I don't want any change due to density, or any change in density or viscosity due to temperature. And then boundary conditions. Okay, so here you set inlet cold, hot. Okay, so you put your value, temperature value, but also turbulence quantities, and that's all. Okay, so at this point we're ready to go. Remember always to set up your monitors. Okay, and let me initialize this case. So probably this is not a good initialization. Let me put everything 0, 0, 0. Okay, and here I go calculate. Okay, so I'm using the standard K epsilon, and let's say that that standard K epsilon is not plotted here. Let's see what it will give us in this case. So as I mentioned, this is a 3D case, but the mesh is not very fine. It's a well modeled mesh, as we mentioned in the case presentation. You can make it also well resolved as one. You have all the dimensions there. So let's monitor a little bit the solution. Let's see what happens. Let's see that we have not bad behavior. Okay, so it's going down. Okay, it's just 40 iterations. And see that here it appears that it will start to stabilize that monitor. Our mouse flow is also oscillating a little bit. Remember, method is conservative, so what is going in is going out. So basically I'm monitoring that imbalance here that should be closer to 0. Still it's a little bit high, but see it's going down towards 0. This is the average Y plus, so I'm not going to expect to have a constant value here, but it can be also a good monitor. And here at the outlet, I have the area weighted average velocity. Okay, so see that this one is kind of uniform, so it's telling me already the outlets, we might have uniform flow. Also at the outlet here, since that is becoming already uniform. And our residuals just going down. So this should converge, not too many iterations, probably, I don't recall, 300. Okay, also, well, we depend on the turbulence model. I don't recall this one, so I will let it run a little bit more and let's see what happens. Okay. Okay, so after about 300 iterations, since that the residuals are stalled, but this is not a problem. Remember, here is what you need to check. So this quantities, this monitor seems to be stable. So let me stop it here. Okay, and the idea here, it was to check the turbulence production in the interior of the domain. So see what we have here. This is the K epsilon case, and see here that here in the middle, it is producing some turbulent viscosity, okay, but see that in reality we have that vortex there that it shouldn't be producing. So see that this one is have the trend to produce turbulent viscosity in the core of the vortex, what in reality should be something like this. Okay, so this is the K epsilon without that curvature correction. You can also check the behavior in these directions. Okay, just to remind you that you can plot some path lines, so you can release something like this, and you can see that what we were looking at here, the velocities are lower. So let me change this one for velocity. So in the center we should have really low, and it's producing very very high turbulence viscosity in the core. Okay, so let me go here, if I put velocity here, outer range. Okay, so see that in the center, see that velocity is very low, and the theory should tell us, the theory tells that if that is the case, why should we produce too much viscosity there? Okay, and this is the problem in this case. So again, if I go back here, turbulent viscosity, see that is producing too much. Okay, so see that in this case, this model, the K epsilon, is not a very good one. Okay, and even probably I think I enable the curvature correction. See that it's not doing a good job. So if you change the model and as you go back to the theory, you will realize that these two are improvement of the standard, just to take into account this effect. So let me go and use the RNG, okay, and let me launch a few iterations, okay, just to show you. So changing the model, we have the typical jump there. So let's wait a few iterations, okay. So let's see what happens. But again, see that here you have an effect here, an effect here. That it seems to be large, but who knows? You need to let it run for a while. Okay, so at this point, let's run. Let's see for what happens in 200 iterations. Okay. Okay, so at this point, if you look at your solution, see what happens here. So see that in this case, see that now we're capturing better here in the recirculation area. See that we don't produce too much turbulent viscosity there. Okay, so this is the ideal behavior that we should aim, and this is everything due to the fact that we're using a better model, but also the curvature correction. So at this point, let's open a new case. Okay, so I have the solutions in this case, and let's open now, for instance, the K epsilon realizable with no curvature correction. Okay, so this one we already know from the theory that should give worse results. So I open in here a pre-computed solution. So see that when I plot the results and take a look at the scales, okay, so see that where values are from 0 to 0.1, okay, but see that is quite large values, okay, with no curvature correction, and see that at the core is also producing too much turbulent viscosity there, which should expect lower values, okay, and see here when we look in the other plane. So now let's change the turbulence model, okay, so remember that you enable those actions there, curvature correction. So if we open now with curvature correction of the pre-compute solutions, okay, we were going to reproduce those results. So basically, if we look at the same plots, see that now we have a completely different behavior. Okay, so see that in the core, turbulent viscosity is very low, then also lower values in the whole planes, in all now the planes there that you see there, we have lower values of turbulent viscosity. So this will add less dissipation to the case. Likely you will resolve better the physics. Okay, so this is in overall the effect of this curvature correction, okay? So the same will happen if you choose a Reynolds stress model. Remember, this Reynolds stress model, because they are more sounded in the sense that you resolve more equations, doesn't mean that they are better, okay? They are very tricky to make converge, okay? So if you run this case, you will find a lot of convergence problems. You will need to use precursor simulations and so on, okay? So you have many options here, so you can play with those options. And as you see, there are no corrections here because the Reynolds stress models, you need to add these production limiters or curvature corrections. They are already in the model. But again, they are very difficult to make converge. So just to take a look at a solution, so see that in the same planes and see that the turbulent viscosity values are very low. So let's adjust the scales and see what we have, okay? So it's something very nice. So see that it's only adding viscosity, turbulent viscosity where you have high strain rates, okay? Where you have that large, the spin tensor, where you have a strong spin tensor. So this is the idea of these models, and these are situations where this model performs very well. Okay, and if we take a look now at monitors, okay, so see that in this case, the monitors remains stalled quite fast. Okay, that is not a digit indication that is wrong or right. Remember that you always need to monitor some other quantities, but generally speaking, to make converge these solvers is very difficult. It's quite tricky, and you need to use precursor simulations and monitor continuously the solution. So see there that you have all your Reynolds stresses that you're resolving besides your standard equations of the turbulence model. Okay, so I think that's all for this case. Again, feel free to play and try to reproduce these results. See you next time. Thank you very much for your attention.